Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Appointment in the cognitive science program, which is even more interdisciplinary than probably those two. Johnny got his degree from University of Texas, I believe, a decade ago, and has been at Indiana since then.
And today he's going to talk about some very interesting work in information retrieval, information filtering, personalization, and frameworks for taking. So,
thank you. Yeah. Well, thank you for coming. Good morning. What I'll try to do is go through my talk. At any point, if you feel that there's things I can elaborate on, please feel free to interrupt and ask questions. I'll do my best, and if there are more things to talk about, we can come back and discuss them at the end of the talk. Basically, what I'm going to be focusing on is a framework or a model, if you like, for information retrieval filtering, which takes into account the three levels of representation, classification, and personalization, which are viewed as part of a single framework and are dealt with in a way that we could study them together or we could study them individually and understand what their impacts are on the overall dynamics of the system. So that's my general outline. As with any university research, it's part of a process which involves other people. So I acknowledge my colleagues, Dr. Mukhopadhyay and Dr. Palakal, and some of my students who have collaborated with me on this project. So I'll start with a general problem definition, discuss some challenges, discuss an architecture, and then go into system level issues and experiments, and discuss some usability type experiments as well, and then finish off with discussions of future work or ongoing work that I'm engaged in. Now, basically, we all know this story, information overload. There's a lot of resources continuously being placed on the net, and that volume is increasing. We're becoming more and more reliant on the web for everyday tasks. What really is important is as we move into this sort of information service-based economy, it becomes basically a career issue, a life issue for us to ensure that we get a persistent, reliable information service. So much so that essentially you can view the web as a utility service. As much as we rely on the water service, on the electricity service, when we hook into an electrical outlet, we don't ask too many questions. We basically assume that we are going to get a certain type of service. Increasingly, we will begin to view the web and the net that way. That's important, but what are the issues? What are the kind of implications for that? Basically, we're talking about persistence. What does that mean? That means that whenever we log into a system, we kind of, especially this, if you think about search, have to reintroduce ourselves to the system. Meaning, if you go into a portal like Google, you have to re-describe what you're interested in, even though you've done the work or done the search a few days ago. There is no persistence. There is no sort of history of information. The service must support regular and long-term use, and it's somewhat related to persistence. It could be ad hoc use, or it could be usage that are based on things that I have certain stable interest around, such as my health, my academic interest. Those things tend to be more long-term. And those need to be integrated in the same service. Customization has to do with presenting information in a way that fits my context. I may be working on my desktop, I move away, start working on a mobile device. well, that service has to be customized for the device without too much degradation in things that I'm interacting with. Has to be also contextualized in terms of tasks I'm involved in. So personalization to me is a subset of customization. I'm not going to talk too much about things beyond that, but I use that as a kind of a broad frame. What are some of the basic service requirements from this environment, from this persistent utility service? Well, we have organization, aggregation issues, classification, transformation of information from one format to another. We have this personalization layer, and then we have issues around presentation, ranking, routing, pruning, visualization, etc. Let's break down those requirements into more specific challenges. Okay, if we just take a look at the data, the types of data we're dealing with, you can take two examples, say biomedical research, where data can be extremely varied. They can run from text to sequence data to three-dimensional structural data, molecular structures. You can take news at a topical level, can be also very diverse. To make things more interesting, sources such as news tend to change quite rapidly. Okay? And then you put in the layer of the user interest may change over time, even though we can make some assumptions about long-term interests. So to kind of further break down this problem and compose this problem, we have this aggregation, classification, organization level. On the other side, we have the presentation level. Okay? To put this in a kind of a formal way, you can think of this as a function where you have here the aggregation layer, content layer coming in, and here you have relevance ranking. Okay? So this is really a mapping function, going from your content to relevance ranking. The issue is going from content to relevance ranking directly is a highly computationally difficult task. Okay? We kind of can guess that. What do? We try to decompose it. Okay? And the way we do this is we go from content to some higher level representation and then map from the higher level representation to relevance ranking. Okay? So we have two functions. And these two functions can be seen here. Okay? This is function 1. We go from content to this higher level representation. From high level representation, we go to presentation. Okay? PAM stands for Presentation Access Management, Document Access Management, or Data Access Management. For each of these modules, so this is my unifying framework, and for each of these modules, we have supporting modules. Okay? We have thesaurus management for representation level, classifier for the classification level, interest shift management, and shift detection for profile layer. Okay? Using this framework has been very helpful because what it allowed us to do is we could come up with, let me just spend a little bit of time on it. What we can do is we can come up with algorithms for representation depending on content we're dealing with and keep the other modules constant and study the impact of this over here. Okay? We can do the same by keeping this and this constant, dropping in different types of classifiers and studying the impact of the classifier on here. Okay? Same for this layer. Okay? We can do these for the submodules as well. Okay? And some of the work that I'm going to talk about, I'll spend some time here, but I'll spend more time here, okay, on the personalization level.
I don't know if it's a color blindness issue for me. I'm not generally colorblind, but I'm having a really hard time seeing the dot on the screen. So when you say here, okay, I'm sort of cognitively lost at that
Thank
point.
you.
I don't know what the here is.
How about this one? Okay. So basically, I was referring to these three modules and how we can study them in isolation and in combination. Okay. So what I'll do is I will discuss some challenges and problems at these levels and discuss some experiments we have done here, and then spend more time and end my talk by discussing this level. Okay. and get into more detail about algorithms here with the profile management level. Okay. So at the representation level, representation classification function 1 level, we have obviously these challenges. Content coming in, we need to somehow represent them in structures that are efficiently computable. We need some kind of features to deal with. This is basically feature space, okay? Labels, terms, concepts. Just using features in a flat way isn't sufficient. We need to also establish associations among features, okay, which is association discovery. So feature identification and association among features are two types of problems. Okay. So this is where we kind of break them down. We do algorithms to convert data elements to computable structures using some type of resource. Okay. We always use resource. Now this resource could be humanly generated or could be machine generated or could be a combination. Okay. Here the same kind of the same problem of taking this content and representing it into higher level structures or classes. Okay. The problem here is basically once we have these representations, how do we find what broad classes or topics those representations belong to, when we could do this in unsupervised way or supervised way. Okay. So if we take the problem of representation, well, we've done some basic stuff that you normally see in IR work, using TF-IDF approaches, using LSA to improve over TF-IDF, and doing clustering to find associations. So there is your standard TF-IDF, and then we've done association using, this is unsupervised clustering, max-min. More details about these approaches can be found. And if, one note that I'll make here, remember the biomedical domain? There's one paper which dealt with the medical literature, and another paper that dealt with news as a resource. And they present different challenges. Yeah.
Are you going to say more about what makes them different?
Yes, because what makes them different is here you can get away at the classification level because the content it doesn't change as frequently as news. You could try supervised approaches at the classification level. Here, no. Okay. Here you have to come up with better unsupervised approaches to do, especially online retrieval and filtering. Okay. And this is an unsupervised approach, and I'm going to present some results and things we've done for experimentation and learning about challenges associated with these issues here.
Are you going to talk about the term-term association stuff?
Not in detail. I can. Those papers are there. Basically, the term-term association is a flat clustering. What we do is we take content streams, we take representative samples from them. Let's say we take 5,000 or 10,000 items, and we convert them to vectors. Okay. The vector conversion relies on some kind of a dictionary or a thesaurus. The thesaurus or dictionary could be generated automatically or as a combination. You could borrow from existing thesauri and use terms in your dictionary. And what you get are relatively sparse, long vectors. Okay? And we apply, generally we prefer unsupervised max-min clustering, where basically you do term-term association. You go from content or document term matrix to term matrix. Okay? You do a matrix conversion. Then you take term association matrix to find centroids or cluster representatives around which documents tend to or content tend to flow together. And you can do an analysis based on centroid to centroid distances, and you can have a threshold or a parameter where you stop the loop when the distances are sufficiently large. Okay? It's a computationally expensive process still, but not as expensive as supervised. Okay? So this calculation is really about, this is the dependent variable. This is how we ultimately determine how well the system produces ranking. Once you have done your classification and representation, and let's assume we have some type of a profile and some techniques to generate profiles, which I'll spend some time on discussing how we do that. After you take those classes, you match them to profiles, and you get a ranking of your items. We use normalized precision to determine how good the ranking is. Okay? This is a pretty standard matrix. We can also do analysis of evaluation how good the clustering is, and you could do that based on the internal measures that I just talked about, where you can calculate centroid distances. You can also calculate for every centroid the average distances of items to the centroid, and you could say, okay, I think the items per centroid or per class are relatively close or tight, and if they're relatively close and the distances across centroids are relatively large, you get good clustering. That's an internal measure. It's not necessarily content sensitive, whereas this measure, this external measure, and one measure is called homogeneity. What you can do is you can take, now for this you need labeled items. Okay? If you have labeled items, you then look at every cluster after the clustering is done to see how many items in every cluster came from the same label. Okay? So basically label the distribution of items per cluster, how heterogeneous is it or how homogeneous is it? Determined based on the labels that have been attached to them a priori. Okay? So that's an external measure, and that can be done too because there are lots of labeled items. And you may be surprised to hear that because I keep hearing from people, where do we find labeled items? There are millions of labeled items. Okay? This is a comparison of classes generated automatically using the association discovery technique, which is the simple technique that I just described. And you can be surprised actually to see how good content you can get automatically. Okay? You can see cell adhesion showing up, cell movement showing up in different form. Motility is movement, cell movement.
Evaluate the quality of these? Do you do sort of a cluster overlap measure?
This one?
Yeah.
What we do is,
Yes.
yes, what we do is we classify, because this is our set of classes. After we classify content into these classes, we see how homogeneous they are, meaning if they came from the same class and tend to fall in the same class here, we're doing a good job. So here what I'm going to present are some experiments to evaluate these automatically produced classes. Okay? So classification accuracy, we measured using homogeneity. The golden set, 0.6, standard deviation is relatively high. Accuracy correlated with filtering or retrieval performance using normalized precision. With higher classification accuracy, filtering improved. So for those classes where homogeneity is higher, we got better normalized precision. Okay? And here's a correlation. This bottom one is a system that has classes that were automatically produced. The top one is a system that has classes that are mesh classes.
One second. What is the x-axis?
The x-axis, basically x-axis are sessions. So we had about 40 sessions, meaning every session of the system, we stream some content through the system. Okay? Generally ranging from 20 to 40 items every session. We push the content through.
And it use that content?
Yes, online, basically. And we online classify the content, online rank content, and then look at the ranking to come up with this normalized precision for every session. Okay.
Are you online regenerating your clusters?
We are online doing, no, we're online doing classification, not regenerating the clusters. We do the cluster generation offline.
So why would you expect an increase over time? Is it just that the articles in later sessions are easier for some reason?
That's a good point, Sue. Why do you think this latency?
So let me get this straight. You build up a set of categories using your clustering, and then you classify. And as you're classifying, somehow your precision is going up.
Yes, because there is another module, right? You remember this module? This is the hidden story. We are talking primarily at this level so far, but this module has a role as well. This is the module which has the profile. The issue is, how is the profile generated, and how is the profile updated? And the profile is a dynamic profile. It changes over time. And that's why you see this latency.
So your clusters don't change, but you are keeping some information for sessions.
Yes. As you push more documents through over time, the profile gets more information about what the user is interested in.
So how do you seed it at session 0? How do you seed the profile?
Profile is seeded, basically it has zero knowledge about what you're interested in.
How do you get feedback about what you're interested in?
That's when I have to talk about the profile. Okay.
Dip in precision?
This dip, why do you think? What do you suspect?
Change interest.
Change in interest could be one culprit. What's another culprit? What is a variable as we push documents through the system? The content of the stream. If the stream becomes very heterogeneous and diverse, there's a drift, topic drift in the stream, the system gets confused as far as how to deal with the very heterogeneous content. Okay? And that's when this dips. And when content stabilizes again, it learns the new sort of topic. If topic drifts into another area, and that's when you get this up coming up.
Excuse me. So I'm a little lost here. Why does my profile or the topic drift have anything to do with matching mesh? I mean, wouldn't that be just purely...
Because we start with a very long list of mesh topics, and your interest may be, number one, a small subset of those terms, not all of them, right? Second, even over the small subset, your interest may change. In certain topics, your interest may be high for a certain amount of time, right? And then after a certain number of sessions, your interest may drop.
Right, but why does that change how your model matches with mesh? I mean, I might change from cell def to being interested in some other topic within mesh. Why does that change how your alignment here with mesh? I don't...
We're not changing the mesh terminologies. We're not changing that. What we're changing is, as more and more content is pushed through, is your interest level in those topics.
Maybe I'm just confused about this graph or the experiment that's being shown,
Right.
which is that I thought that the mesh was the manually labeled topics for this item.
Right.
So sort of an absolute human measured thing. Now here's this automatic thing that is labeling the documents as they're coming through.
Basically, the automatic one, what it does is it takes these classes, which are produced automatically, and once they are fed into the system, they don't change.
Okay.
Okay? So once I start this experiment, right, the class set remains static.
Oh, so hold on. So this is just precision of whatever you search it. Is the solid line mesh then?
Yes, yes. Top line is mesh, bottom line is the other set of classes.
Okay.
So it says the manually done set is slightly better than the automatic, but the automatic is still pretty good.
It's pretty good. That's the story.
You have a baseline, which is where you did none or something.
Sorry?
We'd like to have a baseline which is with random categories or something.
Right. We have that. Not here, but not here.
It also looks like all those little wiggles
Right.
are actually all important.
Yeah.
So if I did a scatter plot of the two against each other, throwing out the session variable,
Right.
my guess is I'd see pretty strong correlation.
Yeah.
So it sort of says that some queries or some questions are just easier than others.
Right. Right. And in fact, what looks like a very different set at first, but as far as the user is concerned, the noise, meaning the difference between this and this, over time doesn't matter because the user, there may be classes that are pretty close to each other. For example, this cell death and apoptosis are synonyms for the same thing. So if I'm interested in cell death, these what looks like two classes are really the same class.
Back to your other plot.
Right.
And here it looks like every little wiggle going up and down.
Right.
Both lines go up and lines
Yeah,
go down.
almost. Yeah. Mm-hmm.
And what I'm thinking that means is that it almost doesn't matter how you do the search.
Yeah.
Just some things they're looking for are going to do better than others.
Yes. Oh yeah. Yeah. True. Because
We're sort of teasing out that.
exactly. Because we are assuming this sort of, service where content may be coming at you all the time, at your system. And what the system is trying to do is to rank the content as they come, and what content are produced, and what's the heterogeneity is not under your control. Okay.
I mean, this graph is showing the performance of your entire, including the...
Yes, exactly.
I think what we're trying to dig at is looking at just the components up till now. And would it be safe to say that the time at position 0,
Right.
for instance,
Yes.
is your baseline if you remove the personalization component completely?
Yes, could. And I'll show you that without personalization. Some results.
Then it will be flat.
Almost flat.
We might be able to...
I think what Ken's saying is it will bounce up and down. There's going to be temporal trends in the content. In some classes, the period of time are easy.
Right, but if you could average it over the
So the
in a way that the
personalization
personalization
component,
couldn't.
but
There's also some content variation.
Yeah.
Right.
I was going to ask you about did you try to correlate with the size of the input, but you seem to have.
I did. And I'll show some results on that. Yeah.
Do you have a baseline that's just sort of raw content matching? So imagine I do no classification, but I just do like a vector space representation of your interests. Maybe we should let you get to the data.
You see, this is without personalization. This is the type of trend you get without personalization.
well, there it seems like there's a downward trend. Well, it's probably just random.
So this is information filtering with no model of what you want,
Right.
right?
The system has no idea what you're interested in. Whereas this one, the solid line, it has a model of what you're interested in. In fact, it's trying to find the model over time. And as time goes, meaning sessions, number of content, number of items it has seen and it has gotten feedback on increases, the profile gets more accurate.
And what are the two curves?
Sorry?
What are the two plots?
Two users, two different users, and these are real users. Okay, let's go back. So you've anticipated some of the issues. So in the classification level, the challenge is, the indexing has to be done pretty efficiently. Indexing meaning grouping of content into high-level categories. And what we've done is we've used supervised approach using a relatively small set of content, but we're doing this with a larger set as well now. The experimental levels were, so we did a direct similarity match with mesh, one classification that used and assumed mesh labels, another classification that did not have the content coming in, were not pre-labeled. They only had the title and the abstract, no labels, but we used this neural net classifier to find the label. Okay. for the content. So we had two levels. First, we do a classification accuracy check. We find that with supervised approach, the classification accuracy improves, error rate drops, standard deviation drops quite a bit. With higher classification, again, we get higher correlation with better performance. This is neural net. This is mesh. This is the golden standard, okay? Because the classification is done totally, handcrafted, okay? And this is automatically classified content. And look at the correlation. It's 0.98, significant correlation. Any questions at this level? So someone asked about stream size. What happens if we change the stream size? And what happens if we change the granularity of the classification level, meaning we change the size of the topic set that you classify into, okay?
I wasn't really looking at the total number of documents, but the size of each document. If there's more content, it might be,
Possibly, sure. But you could get a sense of that, I think, as the stream size as well.
Are the documents kind of varied in sizes, or
They are, but I think, let's see what would happen different from here. If you had more content per document, you'd probably get a better classification. You'd probably get performance, the latency might decrease a little bit, probably. And here's the latency also as a variable. You see, before latency, pre-latency, small number of documents tend to, this is a weird result. You shouldn't get this result because number of documents is very low and you're getting very good performance in stream size. That's counterintuitive because the system really does better over time as more and more documents are pushed through the system. And actually after latency, which is after about 15 or 20 sessions with the system, the trend almost reverses. More documents per session or per stream produces the better result, okay? Which is what you would expect. Post-latency, the standard deviation of performance, look at number of documents, size is 40, standard deviation of performance cross-session. Across session, standard deviation drops greatly. So you're getting more consistent performance, okay, over time. With stream size increasing, you get more consistent, robust performance.
How are documents ordered in the stream?
They just came in randomly, and once they.
Are they timestamped?
Yeah.
So it may just say things about how information is published.
It could be. It could be. They were chronologically, yeah, they were chronologically ordered. But in terms of the interval, the time interval wasn't very large, meaning the content, it wasn't between 1 year going back 20 years. Difference of classification span size, and this is unsupervised classification, where number of classes increased from 22 to 62, and as you increase the granularity of the classification level, you get improved performance. Okay. So let's talk about the personalization level a little bit. Okay, what are the challenges? Basically, as I said, if you want to do this in this multi-level approach where you take documents, you convert them to some type of representation, classify them into larger groups or clusters, and then try to rank them, the way we went about personalizing, we say that, well, you have interest, but your interest doesn't cover all the classes, especially if the class space, the span size is very large. You generally have interest over a small subset of those classes, and your interest may vary over those classes probabilistically. Okay? So how do we model that? How do we build a system to do that? So identification capture profile cannot rely directly or exclusively on the user. Well, Why not? Why do you think that is? Profile generation could be very simple, where basically we ask the user what topics you're interested in, you get the interest values, and you have a profile. But
it depends on how you generate the profile. So
yeah.
if you're doing it implicitly, there might be one answer. If you're asking the user, they might have forgotten, they might have done different ways. But you haven't told us how. I mean, I came in a bit late. Maybe you did.
Right. Well, what I'm saying is directly and exclusively on the user means explicitly. Can we rely on, what I'm saying is, can we rely on only explicit approach? If so, why? If not, why not?
It's a lot of work.
Sorry?
It's a lot of work.
It's a lot of work. Exactly. Right. Basically, the user doesn't want to deal with it over time, right?
Users may not be aware of changing trends in their...
The user may not be also aware of, at a very fine grain level, the changes that are taking place at the user level or also in the domain level. And interest actually over time has to be adaptive and change as new content is found and discovered. So how do we do this? Some of the ways we want to do this is capture interest in a way that links up with this topic discovery and exploration level, provide some level of control to the user to modify the profile, detect interest shifts automatically, and then support some kind of domain visualization or presentation. This is one way we are doing profile generation, profile management. We have a set of categories that are our classes. I'm sorry, I'm using different terms here, but C1 through C9 are our classes. You learn over the classes one level of one vector of values, and each element in this vector, U1 corresponds to C1, tells you how much the user may be interested in this class, a probability value that category 1 is relevant to the user. We also have a second level, which is T1 corresponds to C1, T2 corresponds, which only tries to model one class, the best class, or the best category. Okay? This models the best class, this models the rest of the classes. Okay? The reason we have this two-level learning, okay, is because we want to, this one we initialize with equal probability. This one we initialize with some interest values collected from the user. Okay? Why? Because we want to actually introduce some level of exploration over the category set or the class set. Okay? Even though user may be very sure that these are the topics, these are the classes I'm interested in, we want to have some level of exploration in the system. Because as new content comes in, the user may change his or her mind, and that should affect the overall information that we're collecting about content. Okay? And this is also robust with changes in interest from the user side, not necessarily from the domain side. And what we do is we use reinforcement learning, okay, which is an online learning, as you probably know. It's not unsupervised, it's not supervised, it's kind of a hybrid where we take relevance feedback generated from interaction, we map them to classes, and then once we know the relevance feedback corresponds to individual categories or classes, we update our profile accordingly. Okay? The update here is basically a running average of the probabilities. The update here is using reinforcement learning principles. The way we do this is we upgrade one topic and downgrade the rest of the topics or categories in a way that eventually, gradually, this converges to a unit vector. Okay? So basically, this, I'll show you a graph of how this converges later on.
It doesn't converge to uniform probability distribution.
No.
It converges to like the marginals or the...
It's a unit vector, meaning basically one class goes up to 1, other classes goes down to 0. Okay, that's how it converges. So we've done some experiments with this personalization technique, the reinforcement learning technique. We've used experimental methods where there were actual users. We've also done some simulations. If you want to learn more about the technique, this is the best paper. We have several papers on this technique, but this one is the one that sort of gets into details about how we've done it. Let's talk about a sort of a usability, actual user-based approach to understanding what's going on. I know some people are interested in explicit versus implicit and other sort of hybrid techniques. So what we looked at is we had sort of hand-coded, handcrafted profiles, which we call rule-based. Okay? We had explicit, which is rating, which is not rule-based, but it is explicit in that it prompts the user for information, which we know over long term is not a viable approach because users get tired after a while to give you more and more rating. Well, implicit tries to take account for that and looks at user behavior and user observation, okay, to learn about your interests. And the domain we used a kind of a fun domain, which is mp3.com site. We created a simple interface for people to play music from that site. Yeah.
So the third thing, the implicit option,
yeah.
Did you look at only their behavior within the experiment, or did you have any priors from maybe their documents or email? Or
we only looked at inside this domain. Okay. So basically, this is a representation of a profile, but it also shows the categories going from blues, classical, country, folk, etc. This is a profile of a user. As the user interacted with the system, user can see titles of music, artist, genre, more information. User can rate content and also provide content rating directly to individual items here. So this is over individual items. This is over one session or one presentation. Okay, different types of rating. We basically looked at implicit sources of evidence by looking at users click on the column, users click on artist name, click on genre, various click indicated together, and we used linear model to combine these parameters, and time spent on listening to music per genre as sources of evidence for implicit learning. Okay. And this was a separate function, time spent, because this degraded over time. If users spend less time listening to certain genre, we had a sort of a degradation parameter built into this, which reduced the interest of certain genres. So performance is kind of hard to tell. Everything sort of came pretty close together. But what happens is, you see this line, this is the one that's basically implicit. See, it starts here, gradually takes up, and this, we didn't do this over many sessions. We did this about 5 or 6 sessions here. But if we believe if we increase the number of sessions, this would begin to kind of take off. Okay? And this is kind of a preliminary usability experiment. We want to do more work with this. But it was somewhat promising. I would have liked to see more separation, of course, but we didn't get that. We saw basically this one, which is rule-based, handcrafted, is not adaptive, is asymptotic, comes up, and then sort of stays at this level. Okay? The explicit one with more and more rating increases, which is adaptive. So that's kind of the performance we got.
How come the no profile is so high?
Yeah, it's above 0.5. We have to, I'm not sure. I think with the number of sessions, as user learns more about the different genres, this would drop and stabilizes over certain genres. So this is some preliminary result. We did this over 30 people, and you're looking at aggregate results here. But then we looked at individual usage patterns. This is one user, this is a different user, and we used a different domain to generate these results. The domain here is PubMed data. Okay? And here you get a clear separation for some reason. Okay? And you get also the genres, I think, make a difference. There are many more genres or many more classes in this case. We had many more sessions over time, and you get a much more of a contrast in performance.
But even here, the precision is like 0.3, we'll say.
Right, over here.
That means if you just return the same items to everybody, they're happy 40% of the time?
According to this, yeah. I think because, again, the set of content they're looking at, the screen full is about 30 to 40 documents. Imagine if we increase the number of documents to many more that they have to look at per session. Okay? I believe then normalized precision.
Almost half of the things you show.
Right. Right, but that's because I think partly to do with we're not presenting that many documents per session. If we increase the number of documents, the stream size, I think this would be affected. This proportion would drop over time.
So, can you just explain exactly what's going on in each session here for this?
Sure. Basically, no.
You just present them with.
I can explain it based on this. Basically, what happens is the user. I have an interface. Let me show you. That was done with actual users. So, say user is presented with documents like that. Okay, they can open a document. This is PubMed stuff, and provide a relevance feedback. Okay, and every time they rate or rank the content according to their preference, we update the profile, change the profile.
And the expert users that have some explicit motivation.
They can put that information, initialize the profile before starting the session.
So regarding the difference between the music one and this PubMed one, couldn't one of the differences be that, so you're assuming that the genres you allow classification into actually correspond to interests of the user. So if there's not a genre that corresponds to the music that you're interested in, and it's actually across 4 genres, then
that's one comment I made, that in the PubMed one there were many more classes.
But also that your interest may be much more likely to be focused upon.
Yes.
Because of the type of data, it is much more likely to be focused on a class that you actually have.
Right. Yeah, it's true. So that could be one of the differences because of the high contrast of results, right, that we're seeing. Here's a correlation. What we did, this correlation is kind of important because the types of experiments, the new experiments we wanted to do, which is, what if user starts up with a certain profile and that profile changes over time, that interest changes over time? What would be the impact of that on performance? Well, you can do it with actual users. You can ask them to pretend to be interested in certain genres, and after a few sessions you can tell them, well, why don't you change your mind now and look at some other documents? You can do it, but it's not very realistic. Okay? So what we tried to do is actually simulate users. We created a simulation of this system that you saw the pictures of at the end, which didn't have these nice interfaces. Basically, what we do is we take a profile information like this, and the simulation system can actually take the profile and the interest information and probabilistically generate relevance feedback and rating based on the profile. Okay? So if your interest in certain topics is high, the likelihood that you would give higher rating to content that comes in that matches that topic is high. Okay? It's not an absolute ranking, it's a probabilistic ranking. And turns out you get pretty good correlation with actual users. Okay? So we asked a user to use the system, okay, over time, and we got the profiles from that user, and we fed the profile into the system and generated the results. Okay? And the correlation is pretty close. Okay? So the profile itself changes as new different content comes in and different types of feedback is generated from the profile to adapt to the new content over time, and we get pretty good correlation. Using this as a kind of a confidence builder, we said, okay, we can do more simulation. We went ahead and used simulation techniques to look at, okay, how does profile accuracy and performance are influenced over time. So different types of profiles, concrete, middle, mild to low profile, meaning profiles that had very high probability values in certain topics, almost guaranteed you would get high ranking or rating out of those, versus profiles that had sort of mid-level probabilities, you'd get ranking that fell on both sides, to very low probabilities, just basically unpredictable what types of rating you would get. What type of, basically you can think of these as very sure user, somewhat sure user, user who is not very sure in terms of using, about the domain, okay? And you get different patterns, okay? Concrete is the top one, which basically stabilizes, okay? And you get a user who is somewhat sure, is this one, okay? And this is unsure user, and you see the problem, okay, with the unsure user. And then there is no learning, okay? This level. And over time, as user exposed to, the user may experience change interest is gradual or abrupt. So we wanted to understand what happens if the interest changes not in over long intervals, but over short intervals, and what's the difference in performance. If the change is very abrupt, that makes the learning process harder, okay? How does that impact the profile learning? So this is incremental interest change. You see this is somewhat more stable versus abrupt interest change. But still, you see even in abrupt, okay, which is sudden interest development, what happens, what we did is over sessions in certain topics, we suddenly reduced the interest, the probability values, and ran more sessions. Over certain topics, we suddenly increased the probabilities and ran more sessions, okay, to see how it influences the behavior of the system. Okay. And you see, even over this, toward the end, it again catches up. There are dips in performance, but the reinforcement learning is quite robust. Yes? Oh, yeah.
So I was thinking that if you had a system that's using profiles,
right,
and the previous queries were helpful, gave information,
right,
and personalization would be a win.
Right.
But if I had a model of interest change where the previous queries were in fact not relevant, but counter, they were on a different subject than what I'm now asking for.
Right.
There ought to be a loss. So what I don't understand is why the dip after you change interest doesn't fall below the baseline. Why isn't it worse right after you change interest than to use personalization than to have done no personalization?
Right. For example, here, when I change interest, this dip doesn't go all the way down. Right. Is that what you're saying?
That suggest that there's something wrong with this model that you've used to generate this?
There is something wrong. And what do you think is wrong?
Well, that you didn't change interest enough.
Exactly. But yes.
Well, that was actually my question. Is can you qualify change in interest? I mean, are we talking about I'm in lung cancer,
right?
And then I suddenly change interest to motocross racing, or am I interested in lung cancer and now I'm interested in specific tumor types?
Right.
I was talking about money banks and now I'm talking about riverbanks.
Right. But remember, this interest change is being detected implicitly. This is basically based on relevance feedback generated, simulated relevance feedback, right? So the user, in this case, is not directly giving the information. We're simulating it. Imagine if we have a system where, with the interactive version, where, let's take the tune SIFTER system, where you have a chance to actually tell the system that in this topic, I'm no longer interested in, right? And lower my interest down to this, Whereas in this topic, I'm very interested and increase it. There is a trade-off. And that trade-off, I believe, is how much time the user is going to spend explicitly describing his or her interest chain. If you want the system to learn implicitly, there is going to be this noise. And you can reduce this noise, but you need some other, other sources of evidence.
Still, I'm not clear on the degree. I'm interested. What I want to get is on these stars.
Right.
Specifically, what's the degree of profile change that you're looking at? Is it gigantic or is it small?
No. Basically here, when I say low to high, right? Let's take one of them, which is this guy, which becomes like so. I took something like low to me, the way I represented it and it's described in the paper, is something below 0.4, okay, as probability.
Is it for one category change or is it multi-category change? So if I look at a set of profiles, right, I could have a set of values for that, and then I map onto another profile.
Right.
A different set of values
right.
for those categories.
We looked at both single and multiple. And in the
would you classify a single change as low and multiple changes high? Is that the kind of thing?
No. The change of low to high, in this case, is a change in a single topic from something below 0.4 to somewhere above 0.6. Okay? So we start with a very low interest, like 0.3, and then all of a sudden, where you see a sudden, hike, for example, right there, it goes up. Okay, we change the probability value.
Category that you're showing?
Yes.
Okay.
Yeah. It's a degree of probability change per category. Yes.
But then each data point is also an average over the session, right?
Yes.
Would it be fair to say that during one session, if you push documents to the user, some of them will be on the previous topic or topic of the interest.
Mm-hmm.
So this is why the changes may be gradually, so there is no drop.
Right. Yeah. Exactly.
Even the decrease is gradual.
Right. Right.
This is why it doesn't go below this.
Right. Right.
Because for some of the documents in that session, it was still a good.
Right. 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 It is the case. Yeah. But it would have been different if I stopped the system and explicitly gave the information and said, do not show me documents from this topic or something like that. Then the normalized precision values would be different in subsequent sessions, very different from here. So anyway, this is the last result, which is a sort of simple observation, which is if you initialize your profile, okay, and give it all the information you know about your interest and don't change, this is the type of performance you'll get. So if you're a relatively boring user who doesn't change his or her mind over time versus someone who changes, you start with very high, stay at high, you start with low, but get rating information and that catches up. But there is still some dips and bounces along the way. Okay. So let me also just quickly touch on things that I'm doing right now, which is somewhat interesting, is if you take this model where every user has a profile and they have their own system where they can classify content and look at content and rate content and interact with content, but then you have a network of users where each of them have their own profiles, you can make each system as a kind of a proactive agent-oriented system where you are not just waiting for content to come to you. Your agent can go about looking for content from various sources. You can begin to generate subgraphs or acquaintances from the network by learning about who are the other people who have profiles that are similar to yours, okay? So that you can basically look at topics or content from your acquaintances' perspective. And the acquaintance list can be learned also using reinforcement learning. Okay. And you can also reduce latency and avoid the task of initializing the system yourself. If you identify acquaintances who have similar interests, you take their profile and update your profile, and you start the system from there, assuming you trust your acquaintances. Okay? So we are developing sort of distributed multi-agent systems using this model that I just discussed. That's all. Thank you.
Thanks. We have time for a few more questions now, and Java is around through lunch. It thinks that people want to catch up with me more. So, more questions?
I came late, so pardon me if this is something that you explained.
Sure.
I'm not quite clear what you mean by latency. I had one model of it.
Yeah, basically the latency is, or whenever you see this kind of a pattern, in any of these graphs, you see this most clearly here, for example, from session 0 to session probably 7 or 8, there is this low period where there is a sort of a gradual learning, right? This stage, the early stage of usage of the system, and this is common in any learning system, right, is what we call latency. And this is latency because the system doesn't have information about what areas, what topics or categories you're interested in. Yeah.
On some plots you showed the personalization was just a huge win.
Right.
And then you showed us some averages where it was a moderate win.
Right.
And this sort of suggests that there's some range over users or sessions or something.
Right.
And so that perhaps you were selecting the ones that you showed to us, but is it the case that it sounds like because the averages work out, it must be a win more often than it's not. But it must be cases where it hurts.
Personalization?
And can you figure out in some way which sessions, which queries, which users, when is it more likely to be a win, and use it sort of sparingly?
Well, it hurts only in situations where there are relatively abrupt changes in your interest. Basically, that's... or you make errors, or there is noise in the classification space. So.
You don't know which users are the same users.
Right.
So the one where you showed the smallest difference?
Yeah.
Is that the MP3 set?
Yes, in the music.
Do you think that people are more interested in lots of different music?
It could be. It could be.
You have pretty high base rates there, right?
Yeah.
Like 60 or 70%
Right.
stuff anyway.
Yeah.
It occurred to me that you also had a bunch of established categories that you were forced into anyway.
Yes, because those are MP3 categories. Yeah. We had to use MP3 categories in that system because we're just getting the music and labeling, using their labels to classify them. Yeah.
So I guess one pathological case, you're looking at a graph like this, that if your interest changed every 7 sessions, for instance, you'd be continually bottoming out on your latency and actually doing worse. So, if you, because you would start...
You would basically make the system think you're starting from scratch if you change
that I had the left on before. My question was about the... So you do your clustering and find your classes, and in the MP3 case you had them established, and the PubMed case I guess you had them established there.
Yes.
In the case, like in the medical case, for instance, if you're looking at lung tumours, and then all of a sudden you're looking at a specific type of tumour, or if in the music case you weren't interested in rock, but you're actually interested in like Seattle grunge rock from the 1990s or something, then there's upper limits on how well you can do based on a fixed system, right? It's the proportion of that material that's in the system, because no way of differentiating it. And so without including any kind of, without having a way of including that in your classification.
The system would not be able to discover those
areas. So this will only work if you assume that the topics that you have directly and absolutely correlate with the interests of the user, and that's a really big assumption.
It becomes a problem. I tell you, this is an interesting area, and the paper I have on the news domain, topic detection, that's where the more dynamic you can think of it this way: the more dynamic the stream is in terms of content changes, the more of a challenge this classification level becomes, right? Because if it has this pre-selected hierarchy of or set of topics, that's what you are always hooking into.
The problem's not so much that there's a set of topics that the domain is imposing upon you, but that the user actually has a completely different set of topics that don't align with the ones that the domain is telling you exist.
So we've done some research also. If based on the user behavior, if certain topics get 50% of time positive ranking, 50% of some negative ranking, well, what we try to do is split those topics to see if we get better performance. We've done some work in that area as well. Yes?
A couple of quick questions. One in particular about the data that you're representing here. So most of these charts are domain specific.
Yes.
So one, where do you predict that you'll get a plateau in your relevance, in your user interest on relevance within domain specific?
Mm-hmm.
And then secondly, so we know users are not interested in single domains, and there's probably a time aspect of it, whether I'm home, work, play, but how do you imagine multiple profiles playing across any number of domains, probably the outer limit being 20, guessing.
Well, the first question, in plateau at the domain, sort of using domain as a kind of a scope, tend to be, like 0.75, 0.8. This is a higher than the usual plateau that we see. It gets to about 0.75, 0.8 that's where it sort of begins to plateau out. I don't totally agree that users don't care about, I'm not sure if that's what you're saying, domain-centric systems or domain as a scope. It depends on what the user wants. In some cases, user explicitly wishes to go to a health site, right, and look up information and interact with that site, or go to a travel site and just focus on travel tourism. So it just depends.
Well, and that's what I'm getting at is relevance and the correlate of relevance.
Right.
Is you have to be able to predict what the user is interested in at a given point in time.
Right.
So
right.
My interests, for instance, are really far ranging.
Right.
But usually when I'm with space,
right.
I'm interested within a pretty finite.
Yeah. Exactly. Exactly.
Outside of that.
Right.
It's almost a whole separate profile.
But profiles are not, profiles are not, and that's a good point. I mean, the only way I can answer that is for those types of information needs where we can assume that interest is somewhat stable, right? This type of approach exclusively used would give you pretty good results at 0.75, ultimately at 0.75 precision level, okay? Whereas if you go outside that, where you are searching for things from anywhere or any source, and we have to assume that there isn't really a domain boundary, well, in those contexts, there are still open questions. And I'm not saying that profiles are the only way to do searches in there, but you need to combine. Perhaps what we need to study is, if we do ad hoc plus profile, what kind of performance gains do we get, or do we get anything? Okay.
Thanks, Javed.
Thank you.